Assalamu alaikum, dear student. This is lecture number 2 of week number 10, and we are still continuing the chapter number 8, viscous flow in pipe. So the learning objective of this chapter, we have almost covered all the components, and now we are applying appropriate equations and principles to analyze a variety of pipe flow situations. So we have derived the equations, and also now we are applying the equation in different pipe flow situations. So let's see the topics we are going to cover today: the turbulent velocity profile, the Moody chart, the table of surface roughness, and practice problems. So before this topic, or in the previous lecture, we have covered the practice problem and derivation for fully developed laminar flow. So now we are going to cover, if the flow is fully turbulent, then how we solve those practice problems, or those real life fluid flow situation. So let's see the turbulent velocity profile. So we are fully aware with that. This is the laminar flow velocity profile. The typical velocity profile for fully developed laminar and turbulent flow are given in the figure. Okay, so this is for the laminar flow and this is for the turbulent flow. So note that the velocity profile is parabolic in laminar flow, as it is obvious, and we have derived equation for that, and much fuller in turbulent flow. So this is the shape of velocity profile of the turbulent flow, with a sharp drop near the pipe wall. Okay, so we can see there is a sharp drop near the pipe wall, and after that it's almost uniform. Okay, so this is the difference between the fully turbulent and fully laminar flow velocity profile. So there are some more detail of the velocity profile of a turbulent flow, and we have some specific components or definition of the velocity profile as we move from wall of the pipe to the middle of the pipe. Okay, so you can see here, so we have given name to the different region. Okay, so here you see this is the region, this is called the viscous sublayer. This is the region from where it is just started moving away from the wall. Okay, from here to here it seems to be a straight line. Okay, and it is very close to the wall, and after that it's taking a curved shape. Okay, so this is basically the in between region where the profile is taking a curved shape. So this is called a buffer layer, because it's a mixing of straight and curved region. So this is called a buffer region, and right after that it is called a overlap region, and then it is a fully turbulent region or fully turbulent layer. Okay, so let's move on. The turbulent flow along a wall can be considered to consist of 4 regions. Okay, so these are basically consist of a 4 region, from surface of the pipe wall to the center of the pipe by the distance from the wall. Okay, so the viscous sublayer, the first layer, which is from the pipe surface to the straight line, you can see. Okay, so this is called a viscous sublayer, where viscous effects are dominant. So here in this region the viscous effect is dominant. Okay, we can see. Okay, and flow is streamlined. Okay, so here we can see the viscous effect is prominent. Okay, then after that there is a buffer layer. After that, from its moving is started away from the wall. Okay, so viscous effects are still dominant, it is still very close to the wall. Okay, but however turbulent effects are becoming significant. Okay, but the turbulent effect is also increasing. Okay, here you can see it is started increasing. So now the overlap region or the transition layer or the inertial sublayer, the turbulent effect are much more significant. You see when you move from here to here, okay, so the viscous effect is reduced and the turbulent effect is dominant. So the turbulent effects are much more significant but not dominant. Okay, but still it is significant. Okay, after that, okay, when outer layer turbulent effects dominant over molecular diffusion or viscous effects, when it starts moving from the average velocity region. You see this is the average velocity when it's moving forward from here to here. So in this case the viscous effect is reduced and the turbulent effect is dominant. Okay, so this is the four different region of the velocity turbulent velocity profile. So now for the turbulent velocity profile, or basically if the flow is turbulent, so the important is we cannot use or we cannot determine the friction factor which is occurred due to the viscous effect in the and the turbulence occur. We cannot use a friction factor, we cannot determine the friction factor by using the laminar equation, which is 64 over Reynolds number. Okay, but then how we can determine the friction factor for the to calculate the head loss? We use basically a chart that is called a Moody chart, and Moody chart basically depends upon three different dimensionless numbers. Okay, so what are those dimensionless numbers? So the friction factor in fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness. Okay, and the ratio of the relative roughness, okay, and the diameter, which is the ratio of the mean height of roughness of the pipe to the pipe diameter. Okay, so one is the Reynolds number. There are three dimensionless number: the friction factor, the Reynolds number, and the relative roughness. So these are the three dimensionless numbers that we have basically gathered in one single chart that is called a Moody chart. We will see some more detail on Moody charts. Okay, so it is no way to find a mathematical closed form for friction factor by theoretical analysis. Therefore all the available results are obtained from the Payne Stanking experiments. Okay, so by doing the experiments, okay, what exactly he did, the most such experiments were conducted by Prandtl student, okay, in 1993, followed by the work of others. The friction factor was calculated from the measurement of the flow rate and the pressure drop. Okay, so the friction, we will see more in detail. The friction factor was calculated from the measurement of the flow rate and the pressure drop. We increases the flow rate and we observe the pressure drop. Okay, so how the pressure drop is varying as we increasing the flow. Okay, and the flow in that case, okay, if we increase the size of the pipe and we changing the different diameters. Okay, we will see what is the Payne Stanking experiment. Okay, functional forms were obtained by curve fitting experimental data. So whatever the result we got by increasing the flow rate and calculating the pressure drop, we basically plot in a curve form. Okay, so finally the Colebrook combined the available data for transition and turbulent flow in smooth as well as rough pipe in the Colebrook equation. So this is basically the Colebrook equation. So what exactly he did, he basically combined the relative roughness and the friction factor. So the relative roughness is for the different pipe surfaces. Okay, so the relation between the different pipe surfaces and the Reynolds number and the friction factor is basically combined by the Colebrook equation. So this is for the turbulent flow. If you want to find out the friction factor for a turbulent flow, so this is the equation which is called Colebrook equation. We can use it. So since here we cannot separate the friction factor, so we have to follow a iteration method. Okay, we can assume any value if left hand side and right hand side are equal, so that would be the exact value of the friction factor for that particular case or flow. Okay, so after that, in we can say in 1944 the Moody reduced diagram into the form commonly used today, called Moody chart, given in the appendix A12. So finally the Moody he basically developed a chart by using three different dimensionless number, which is friction factor, relative roughness and the Reynolds number, and he developed a chart. This is called a Moody chart. So this chart is applicable for any type of flow, any type of fluid, or any diameter or any type of surface of the fluid. So this is for any velocity, for any flow, this chart is enough. Okay, so you see, so we can differentiate this chart into three different region. So this is the line is basically, you see, in the vertical axis, this side we have a friction factor. This friction factor is also called a Darcy friction factor. Okay, so this Darcy friction factor F is equals to 64 over Re is for the laminar flow, and the turbulent flow we have already seen a Colebrook equation. Okay, and this is basically, this is the region, it starts from here. You see, this is the 4000. Okay, this is the 4000 region. So this is the region started from 4000. So this is the turbulent flow region. Okay, and this is a transition region. Okay, in between this is a transition region. So if the flow is laminar, so we can get the any value of F by using this line. Okay, if you have, because if you have a 2100 below 2300, so we can use this curve, we can use this chart, or also we can use the equation F is equals to 64 over Re to calculate the Darcy friction factor by using, you see, this is line and it is indicating F is equals to 64 over Re. So this line is for the laminar flow, and you can calculate for any Reynolds number below 2300, you can calculate the Darcy friction factor or friction factor. If the flow is above, okay, if the flow is above 4000 or in the turbulent region, so we need another component which is called a relative roughness, E by D ratio. Okay, E by D ratio is the, E is basically indicating the surface roughness, or here you see the smooth pipe. So this is the first line which is very at the extreme. This is the most smooth pipe which have a relative roughness is equals to 0. So as the relative roughness is increasing, you see the curve is increasing and the friction factor is also increasing. Okay, because the Reynolds number, as you go the Reynolds number up, so this is the friction factor. Even for the same Reynolds number, if the roughness, relative roughness is less, so this is the friction factor. As the friction factor will increase, the pressure drop will increase, because the pressure drop is directly proportional to the friction factor. Okay, so to calculate the friction factor for the turbulent flow, what we need to do, first we have to calculate the Reynolds number, second we need to know the relative roughness. So how we can calculate the relative roughness? This is basically indicated by E or epsilon. Okay, so epsilon is different for the different piping material. If it is a glass or plastic, you see, we have a different value, and we measure in feet or millimeter. Okay, if diameter is in millimeter, so we will take this value. If diameter is in feet, we will take this value. Be careful. Okay, whenever you take a relative roughness, so don't take any value. Take in which unit the diameter is given. If it is given in meter, so you must convert this millimeter into meter and then calculate the relative roughness E by D ratio. So whatever the E by D ratio you got, okay, so here you see the E by D ratio is increasing. This is 1, this is 001, so this is increasing 005, okay, 001, as you see, and here E by D ratio is increased up to 0.05. Okay, so if once you know the Reynolds number, you can intersect the line to the relative roughness E by D ratio. So if it is 10 raised to power 6, come straight, and if it is 0.002, so you intersect this line and then just draw a horizontal line and intersect this side. So this would be the value of friction factor you can calculate by using this chart. Okay, so the Moody chart presents the Darcy friction factor for pipe flow as a function of Reynolds number and relative roughness over a wide range. It is probably one of the most widely used, accepted and used chart in engineering. Okay, this is basically a chart which is used in the field as well. Although it is developed for circular pipe, it can also be used for the non-circular pipe by replacing the diameter by the hydraulic diameter. We know how to convert the cross section into hydraulic diameter. Okay, the authenticity of this chart, both Moody chart and Colebrook equation are accurate to plus minus 15% due to roughness size, experimental error curve fittings of the data, etc. Okay, so this is a trustable chart that we can use to find out the friction factor. Okay, now we see the equivalent roughness value for a new commercial pipes. Here you see there are different type of piping material: glass, plastic, concrete, wood stave, rubber, smooth, copper or brass tubing, cast iron, because these are the material normally we use to make a pipe. Okay, so here is the roughness in feet, or here is the roughness in millimeter. Okay, and here is the relative roughness. So you see, as the relative roughness is increasing, the friction factor is increasing. This is it showing here. Okay, so once to calculate the turbulent flow, you must know the roughness of the pipe surface you are using. If it is a glass or plastic, or if it is very smooth, so in that case the roughness would be 0. Okay, for the smooth surface finish. And here the type of the fluid flow problem we are going to see in this turbulent, in the case of fully developed turbulent flow. So here you see we have a 3 type of problem types. We have a 3 types. If the length, diameter and volume flow rate is given, so we need to either find pressure drop or a hydraulic or the pressure or the head loss. If length, diameter and pressure drop is given, then we have to find out the volume flow rate. If length, pressure drop and volume flow rate is given, then we have to determine the diameter. So these are the 3 type of problems, okay, that the items given and item to be determined. So let's see and find out some problems. So here you see, determine the head loss in a water pipe. So here we have to find out HL. Okay, HL means delta P or HL, you can say that. So water at 60 degree Fahrenheit, this is the water properties at 60 degree Fahrenheit. As I said to you earlier, if these properties are not given, you can calculate these properties by using the table, material properties of water at 60 degree Fahrenheit or for any fluid. Okay, is flowing steadily in 2-inch diameter horizontal pipe made of a stainless steel at a rate of a 0.2 feet cube. Determine the pressure drop and head loss. Okay, so you see everything is given, Q is given, diameter is given, okay, and the required pumping power input for the flow over a 200 feet long section of pipe. So we have a 200 feet long pipe, L is given, q is given, v dot is given, and d is given. Okay, so we have to determine head loss, okay, or delta p. And this is the figure. This is a 200 meter pipe. This is a constant diameter pipe, is a 2 inches, and this is the flow. This is the 0.2 meter feet cube per second is the flow. So here most of the units are given in feet in FPS system. So we will solve this problem in FPS system. Okay. To solve this problem, we have to find out the head loss, and we know the formula of the head loss. Okay, so before that we have to make assumptions. Okay, so these are the assumptions are given. Okay, in the previous problem we have already discussed the assumptions to be made. Okay, and what are the assumptions we have made? The flow is steady and incompressible, the entrance effects are negligible, as I said to you earlier, and thus the flow is fully developed. Okay, so once the flow is fully developed, either it will be laminar or turbulent. The pipe involved no components such that bends valves. Okay, so there is no component which drops the pressure other than the surface roughness. Okay, one more thing you must keep in mind: the pressure drop in the pipe is called the major pressure losses. Okay, and the pressure drop due to the components like bends, valves and connectors are called minor losses. Okay, so the piping section involve no work device such as pump or turbine. So these are the assumptions we have made, and these are the properties of the fluid we have noted. So now we have to find out the head loss or the pressure drop. So we know the formula. So before applying the formula, we have to determine the flow, whether it is laminar or turbulent. So we have to find out the Reynolds number. To find out the Reynolds number, this is the Reynolds number, and for the Reynolds number we need rho, v, d and mu. So d is given, we know already, is a 2-inch diameter. Mu is given here in the properties of the material. Rho is also given in the properties of material. Only thing which is unknown, that is velocity. So velocity we have calculated by using the flow to the volume flow rate. So volume flow rate Q is equals to VA. So cross section area, since the diameter is given, so we calculated the cross section area and divide the flow rate by using by cross section area. So we calculated the velocity, which is 9.17 feet per second. So now it is easy to determine the Reynolds number, and we substituted all the values. Okay, so since here you see the diameter is given into inches, but technically it is supposed to be in feet, so we convert it into feet, 2 by 12. Okay, so make sure you have converted all the data properly, all the units converted properly into the right system of unit. So Reynolds number we calculated is 126,400. So it is much greater than the 4,000. Okay, so here, which is greater than 4,000, therefore the flow is turbulent. Okay, so it is determined. So we cannot use R is equals to 64, F is equals to 64 over RE, we cannot use anymore. For the turbulent flow, the relative roughness of the pipe is calculated. So now in that case we need a relative roughness, any epsilon by D or E by D. So that is E by D. So what is the relative roughness and what is the type of the material we are using, we can see. So here you see stainless steel pipe. For the stainless steel pipe, what is the relative roughness? Go back to the chart, let's see. For the stainless steel, you see this is the stainless steel, since we are dealing in feet. Okay, so that is 0.5 times 0 into 7. Okay, 0.000007. Okay, and divided by D, diameter. Okay, so here you can see the epsilon by D, 0.000007 over 2 by 12. So this is epsilon over D. So by using this, we substituted these values here. Okay, we are using first we are using a Colebrook equation. Okay, so that you can understand that how we can use equation and how we can use a chart. So both you must know. Okay, how to use equation and how to use chart. So here we are using a Colebrook equation. So this is the equation we have. Epsilon over D we have put the value here. okay, and Reynolds number we have calculated, we have inserted here. Okay, so now we both side we have f and f. Now we have to determine the value of f by trial and error method. Okay, so take any value of f, okay, which is less than 0, okay, and put trial and error method and calculate the value of f. And by using trial and error method, using a equation solver or iterative scheme, the friction factor is determined to be f is equals to 0.00174. okay, so if you take f is equals to 0.0174, the left hand side and right hand side will be equal. Okay, so that will be the, when the left hand side and right hand side are equal, so that value will be the value of friction factor. Okay, so once you know the f, you can easily calculate the head loss by using this formula. Okay, f is known, L is known, D is known, velocity you have calculated, G is known. You inserted the value, you have calculated the head loss in 27.3 feet. Okay, so here also you can calculate the pressure drop by using the same formula. Okay, so the head loss, how you can calculate? If you multiplied the head loss with the rho into G, rho you know, G you know, if you multiply it with the rho into G, you will get the value into PSI. Okay, because all the values are in fit, is a fit or in pound. Okay, so this is the value of the okay. And finally you want to calculate the pumping power. So pumping power you can calculate, you can multiply the volume flow rate by the pressure drop. Okay, the pressure drop you have calculated, if you multiply it with it, you will get the pumping power, which is 461 watts. Okay, so therefore the power input in the amount of 461 watt is needed to overcome the friction losses in the pipe. Okay, so the also you see the same value you can calculate it by using the chart. Okay, so let's see and how we can calculate that. So here you can see it is, they have calculated f is equals to 0.0172 by using the Moody chart. Okay, if you go to the Moody chart, you the value will be equal to 0.0172. Okay, so let's see and see how we can calculate this. So you see here our Reynolds number is 126400. Okay, and here it is relative roughness is 0.000042. So let's move on to the Moody chart. Let's see. Okay, this is the chart. Okay, so here we have what is this? Here you see. Let's move on to the problem. Or here we have the problem. Okay, this is the problem. Okay, so this is the Reynolds number. What is the Reynolds number? Reynolds number is 1.2 into 10 raised to the power 5. Okay, 1.2 into 10 raised to the power 5, and this is 000042. So let's move on to the Moody chart. 1.2 into 10 raised to the power 5 is the Reynolds number. So let's see how it is. 1.2, this is the 10 raised to the power 5. Okay, so 1.2, so this is 10 raised to the power 5, and this is 1, and this is 1.2 somewhere here. Okay, so go up from here. Okay, go up, and 0.00004. So this is going to be 0.00005 somewhere here. Okay, so this is the curve. The curve somewhere is going to be here. Okay, the curve is somewhere parallel to this line. Okay, so this is the line, this is the line, this is the line just below it, and take the Reynolds number. This is the Reynolds number. We are going to 1.2. Okay, here, and this is the line. So go straight and go straight. It will be somewhere here you can see it will be 0.15, 0.16, 0.17. It is coming somewhere here. So 0.171172 somewhere we have the value. Okay, it is coming somewhere here. Okay, so I think it is clear to you now that how to calculate the Darcy friction factor by using the Moody chart and by using the Colebrook equation. Okay, so here this is the equation we have. Okay, so this is how we have calculated F. So in both, once you know the F, the value of delta P and head loss and pump is the same procedure. Okay, so now let's move on to the another problem. Air at an standard condition flows through a horizontal 1 feet by 1.5 feet rectangular wooden duct at a rate of a 5000 feet cube per minute. Determine the head loss, pressure drop and power supplied by the fan to overcome the flow resistance in 500 feet of duct. So here we have a rectangular duct, it is not a circular duct. So let's see, and we have to determine the head loss, pressure drop and the fan power. Okay, so here is the duct, the length and width are given. Okay, and this is length of the width and height is given, and this is length is 500 feet. So to solve this we need to know, we know the head loss formula. This is the head loss formula. So what we need to determine, we need to determine the hydraulic head. So first we are going to determine the hydraulic head, which is 1.2 feet. Once you know the hydraulic head, we are need to determine the flow. So what is the type of flow? Okay, so to determine the flow we have to use the Reynolds number. For the Reynolds number we need velocity, because the volume flow rate is given. So we calculated the velocity, which is velocity, you see the volume flow rate was given in feet cube per minute, but it is supposed to be in feet cube per second, so we converted into feet per second. Okay, we converted into feet cube per minute into feet cube per second. Okay, so here we calculated the velocity, which is 55.6 per second. Now the hydraulic diameter is known and the velocity is known. Now we can calculate the Reynolds number. Okay, so for the Reynolds number, we calculated the Reynolds number for the hydraulic diameter, which is 4.25 into 10 power 5, so which is much greater than the 4000. Okay, that means the flow is turbulent. And from the table, the coefficient of roughness we have calculated, which is 0.006. Okay, because it is given a range 0.006 to 0.003. So we have taken an average. For the wood, because of good finish, less finish. Based on that, there is a range for this. Okay, so we have taken an average, which is 0.0018, the epsilon. So now the relative roughness, the roughness divided by the hydraulic diameter, we got the relative roughness, which is 0.0015 from the figure 8.20. F is equals to 0.002. Okay, now the Reynolds number are known and the relative roughness is known. So you know both the values, you can easily calculate the friction factor. Once you know the friction factor, you can calculate the head loss. So what is the formula of the head loss that we have written at the beginning of the problem? So this is head loss. You can see what was the formula. This was the formula we have written. So everything is known, F is known, everything is known. So we have substituted the value, and head loss we finally got 440 feet. Head loss is too much. Okay, so for the horizontal pipe, okay, for in case of the to find out the pressure drop, okay, this is the energy equation we are using. In this case we are considering alpha 1 and alpha 2 are 1. Okay, so V1 and V2 is we are considering, since we have a same diameter or a same cross section, the velocity is not changing. Okay, and since it is a horizontal pipe, so Z1 and Z2 is also same. So equation is going to be reduced. So P1 minus P2 is going to be gamma L. Okay, so finally the pressure drop we calculated is 0.234 psi. Okay, so now if you multiplied this with the volume flow rate, okay, so we will get, if you multiply with this the volume flow rate, we will get what? We will get the power which is 5.11 HP, or you can convert into watts also, but since we have to calculate the fan power, so normally we discuss the motor of the fan in HP. Okay, so this is how we solve the problem.